In this video, we're going to be looking at topic 1G, covalent bonding, and we're going to be focusing on the double outcomes as part of the IGCSE chemistry course from Edexcel. So what do we have to know for this topic? Well, we'll be looking at how we form covalent bonds, what that actually means in terms of electrostatic attractions, looking at dot and cross diagrams for covalent bonds, why we have specific properties such as low melting points and boiling points, as well as looking at the intermolecular forces, our giant covalent substances, as well as conductivity and the different structures. So what is a covalent bond? Well, the difference between a covalent and ionic was ionic had a metal and a non-metal. For a covalent, we are looking at two non-metal atoms. And this time, instead of transferring, the electrons are shared. So for ionic, we had a metal and a non-metal, and the electrons were transferred. For a covalent, the electrons are shared, and we have this between two non-metal atoms, and we get a strong electrostatic attraction. Now remember, electrostatic attraction just means an attraction between a positive and a negative, and in this case, it's between the positive nuclei, which is the plural of nucleus, of the atoms, and the negative shared pair of electrons. So what happens is the electrons sit in between the two nuclei, and the attraction for both of these is going to hold the two together. So how do we actually draw this? Well, if we have an atom where we have our outer shell with our nucleus in the centre, that is positive. Our other atom is going to overlap with our first atom like that, and of course this one also has its nucleus, and in the centre of this overlap we have two electrons, and that is the shared pair of electrons. So our electron clouds or our energy levels overlap for covalent bonding, and then the two electrons are shared between the two atoms, and the attraction between this shared pair and the nuclei is what holds the two things together, and this overlap is known as a covalent bond. Now, with some exceptions, most atoms want to have 8 electrons in their outer shell. Now, we're not going to focus too much on the exceptions just now. We're going to focus on the ones that do want 8 outer electrons. And we call this the octet rule. And the reason that they want 8 outer electrons is they want to be stable like a noble gas. Having a full outer shell gives an atom stability. So what the atoms will do is they will share their electrons between them to allow both to have a full outer shell. And what we can do is we can show this using a dot and cross diagram. So this is an example of a dot and cross diagram for a covalent substance. You can see that we've got hydrogen and chlorine, and rather than seeing a transfer, we see that overlap here. And that overlap now means that my electrons are being shared. Now, hydrogen only wants 2 electrons in its outer shell because it only fills the first shell, whereas chlorine wants 8, and when it shares the extra electron from hydrogen, it now has 8 electrons in its outer shell, so now it is stable. And we can draw a dot and cross diagram using the target diagram, like at the top, or we can show just the outer electrons and not have to draw the circles. Again, we're showing that one set is dot and one set are crosses to show that they're coming from 2 different atoms. We could also show it in Cl2, again showing all of the electrons and getting this overlap, and then sharing electrons. Or I can draw it with just the symbols and then the electrons around it. Either one would be perfectly acceptable in an exam. So let's look at some examples of how to do this. So if we have a carbon and a hydrogen bonding together, we have methane. So what we do is we draw our carbon in the centre, and we write C in the centre for the symbol, and we put our 4 outer electrons like that. Now what we want to do is, because it has 4 unpaired electrons, it means it can form 4 covalent bonds, or we can form 4 overlaps. And by showing these overlaps, this is how we form our dot and cross diagram. So it's going to overlap with hydrogen, and we draw it like that. So we have our 1 electron from the hydrogen as our dot, and it is overlapping with our cross here. So now those 2 electrons are being shared. And the same thing happens for each of the 4 unpaired electrons, showing the overlap and showing what element it is. And now when we count, that outer shell of carbon now contains 1, 2, 3, 4, 5, 6, 7, 8 electrons. So now this is stable. And if we wanted to write out the formula for this, we just count. We write we have 1 carbon and 4 hydrogens, or CH4. Then we move on to ammonia, and we can write out the dot and cross diagram for this as well. So our nitrogen atom is in the centre, and we know that it's in group 5, so it has 3 unpaired electrons. Because I fill in my 4, and then my 5th is going to go and pair up, giving me 3 unpaired electrons. Again, these can bond with a hydrogen, giving us that overlap, and showing the hydrogen's electron as a dot, and the fact that these 2 electrons are both within the overlap means they are being shared, and now nitrogen has a lone pair of electrons and then 3 pairs that are being shared. So we form NH3, and the nitrogen now has 8 outer electrons. Another example is water. So water has oxygen as its centre atom, and we know that oxygen is in group 6, so we draw our 1, 2, 3, 4, 5, 6 outer electrons, and we're going to bond it with hydrogen. So we draw our overlap with our dot for our hydrogen electron, and again overlap on the other side with our hydrogen electron. Now our oxygen has 8 electrons. It is now stable, and I have a formula of H2O. Now ethane is slightly more challenging. So ethane has the formula C2H6. The bonding is very similar to what we saw for methane earlier. However, there is also a bond between 2 carbon atoms. So our dot and cross diagram is just slightly bigger. So we draw our first carbon, and we do 1, 2, 3, 4. And then we draw our second carbon, and we get an overlap between the 2 carbons. And I'm going to draw my electrons here as circles. So now these 2 carbons share a bond. Then I can add in my 6 hydrogens, and they overlap with the 6 unpaired electrons that are left over. So I have 1 at the top, 1 on the left, and 1 at the bottom of the first carbon. And then for the second carbon, I have the same thing. 1 at the top, 1 on the right, and 1 at the bottom. And now my formula is C2H6. Now, when it comes to covalently bonded substances, there are 7 key substances that you have to know, and these are known as the diatomic elements. Now, diatomic can be split down into 2 parts. The di means 2, and atomic means atoms. So it simply means that these exist as a molecule of 2 atoms that are covalently bonded together. Now, we can get other substances that are diatomic, but only these 7 elements are diatomic, meaning it is 2 atoms of the same element bonding together. So, for example, something like HCl is diatomic, but this would be a diatomic compound, not a diatomic element, because our 2 substances are different. So for the 7 diatomic elements, what you should be able to do is to memorize them and then be able to draw out their dot and cross diagrams. So the 7 are hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. So you can see that as group 7 plus hydrogen, nitrogen, and oxygen. And a way to remember it, you could use a mnemonic like have no fear of ice cold beer, or I bring clay for our new house, just in a different order. There are lots of different mnemonics to help you memorise these. And for hydrogen, fluorine, iodine, chlorine, and bromine, they are all going to bond in the same way. So if I take my chlorine, I'm going to squeeze it in at the top here. My chlorine has 1, 2, 3, 4, 5, 6, 7 outer electrons. It can overlap with the other chlorine, which also has 7 outer electrons. And then the two things together now both have 8 electrons in the outer shell. And we see that same arrangement for the 5 that I have ticked there. Okay, they all have one covalent bond, one overlap with one set of electrons. Now the difference, however, for oxygen and nitrogen is that they can contain what we call multiple covalent bonds. And what that means is rather than one bond between them, for example for oxygen, it has what we call a double bond. So how do we draw that? Well, we draw our outer shell of oxygen, and we draw our 2 electrons, sets of groups that are already paired, and then I have my 2 unpaired electrons that sit in the centre here. And when that overlaps with another oxygen, we have those 2 pairs that already exist, and then the 2 unpaired electrons form a bond with the 2 unpaired electrons from the first oxygen. So now, rather than one covalent bond, we have 2 covalent bonds. And that's because we have 2 pairs of electrons in our overlap. So we call this a double bond. And nitrogen has what we call a triple bond. And each of these lines in our diagram here are just representing one of these covalent bonds. So for nitrogen, again, we draw our overlap over 2, and then we have N in the centre, and we have our one lone pair of electrons that's already paired up and exist, and then we've got 3 unpaired electrons that all exist in the overlap, and that gives us 3 covalent bonds because we have 3 pairs of electrons in the overlap. In an exam, you could be asked to draw these out, so it is important that you do practice how to draw the double and triple bonds. And it just simply means you have more than one pair of electrons in your overlap. And we can then apply that same information to a dot and cross diagram. For example, for carbon dioxide. Each of the carbons has 6 electrons, and the carbon in the centre has 4. So what happens is each of the oxygens will share 2 electrons with 2 electrons in the carbons, and we get a double bond on either side. So what does that look like? Well, we have the carbon in the centre, and we have an overlap with the oxygen. And our carbon has its 2 unpaired electrons on either side, so all 4 then split into 2 pairs, and they then overlap with the oxygens, and the oxygen's 2 unpaired electrons sit within that same overlap. And that then gives us in each one 2 covalent bonds, or a double bond, because I have 2 pairs of electrons in the overlap. And we can see that here, where we have a double bond on either side of the carbon. Now, as I mentioned earlier, there are some exceptions to the octet rule, and that's when we have less or more than 8 electrons. Now, we don't need to go into too much detail about this now. This is something that you will cover more at A level. But if we look at boron, for example, boron only has 3 outer electrons because it's in group number 3. So if all 3 of those electrons pair, then it can only have a maximum of 6 electrons in its outer shell, because it doesn't have space, or it doesn't have a space to pair with that 4th set of electrons. It only contains 3 unpaired, so it can only form 3 bonds. Sulfur, however, is a little bit different. Sulfur can bond with oxygen, and it can actually expand to make 10 electrons in the outer shell. Some substances can even make 12 electrons in the outer shell. But as I said, that's something that we will discuss more at A level. What you need to know is the octet rule, where atoms want to have 8 electrons in the outer shell. Those are the types that you're going to be asked about in the exam. So I do strongly suggest that you do practice drawing out dot and cross diagrams, because they do come up in the exam and they can be worth up to 2 marks. Moving on now, let's look at the different types of structures. So within covalent bonding, there are 2 different types of structures that can be formed depending on the elements that are bonding together. The first is known as giant covalent, or sometimes known as covalent network, but Edexcel use the term giant, or there is molecular covalent, sometimes known as simple covalent or discrete covalent. All these words mean the same. So we're talking about, for molecular, we have a fixed number of atoms. For example, with water, we always get 2 hydrogens and 1 oxygen. Comparing that to then giant covalent, this is when we have no fixed number of atoms. So we have this lattice structure being formed. And we met the lattice structure back in ionic bonding when we looked at the ionic lattice, and we said at the time that they can have varying numbers, and the same concept applies to giant covalent. The only difference is that this time they're bonded covalently instead of bonding ionically. But this is no fixed number, and an example would be silicon dioxide, or SiO2, meaning for every 1 silicon, I have 2 oxygens. And these 2 different types of structures then have very different properties, and you need to know each of the different types of properties for the 2 structures. So if we start off by looking at covalent molecular and we look at some of their examples, they are small structures that have a fixed number of atoms, as we said. And examples could be water or ammonia, or something known as fullerenes, or even our diatomic molecules. So what do we mean by fullerenes? Well, fullerenes are allotropes of carbon. And an allotrope is just a chemical word for a different type of carbon. Carbon is a very special substance and a very special element because it actually bonds in a number of different ways depending on the situation that it's in. So it can actually have 3 different types of structures, and we will look at each of them here. So the first one is a fullerene. Now, we don't go into a lot of detail about this in GCSE. It's just something that you need to know exists. And these contain either 60 or 70 carbons, and they're in the shape of a football or a soccer ball. And they are what we call discrete molecular solids. So these substances of carbon will always contain 60 or 70 carbon atoms, all covalently bonded. Another type of covalent molecular substance are diatomic elements. So we've seen the 7 diatomics that exist as our gases our liquids or solids at room temperature, and these are covalently bonded together. Again, these are fixed in their number. They only contain 2 atoms, so they are covalent molecular, very small substances. And within all of these covalent molecular structures, they are joined by these strong covalent bonds. Now, when we're taking into account the different properties, we're not actually going to be talking too much about the covalent bonds themselves. We're going to be focusing more on something known as the intermolecular forces. And that simply means the forces in between the different molecules. So for example, in our diagram here, these are all water molecules. So we have our strong covalent bonds that join together our hydrogen and our oxygens. But then within our substance that contains lots of hydrogen molecules, we get some attraction between the different molecules, and these are known as intermolecular attractions. And these, whilst they are electrostatic attractions, they are quite weak. And that's something that's going to be very important when we talk about the properties of covalent molecular substances. Comparing that to our giant covalent networks or giant structures, again, the most common ones are carbon. And this is the two other ways that carbon can exist. So we've seen fullerenes, which are covalent molecular. Now, in the giant network structures, they can exist as diamond or as graphite. And whilst these are both made up of carbon, they are very, very different substances. And you would know that just from your common sense. You've probably all seen, either maybe in real life or even in a picture, a diamond, and we know how hard these substances are, and they're very, very tough. Whereas graphite is what we find in pencils. So what you would call the lead of a pencil isn't actually lead, it's actually made of graphite. So we know that it is a much smoother substance, it can be broken easily, and that's completely different from diamond. And the reason that they have such differences is to do with the way they bond together. So in diamond, we have each carbon atom forming 4 covalent bonds, and it forms a structure like this. So we know that carbon has got 4 outer electrons, and each one of those overlaps with another carbon. So we start to build up this giant 3-dimensional structure that has got all of these carbons all bonded together, and it's quite difficult to draw, so you're not going to be asked to draw in an exam, but you may be asked to describe it. And it's saying that a 3D structure with this giant network of our carbon atoms all overlapping, and we have 4 bonds between each of the different carbons. Now we compare that to graphite, and graphite is slightly different. Graphite only forms 3 covalent bonds with 3 other carbons. So again, it doesn't change the fact that carbon has 4 unpaired electrons, but only 3 of them are going to overlap. That now leaves us with 1 electron that has no covalent bond. And what that electron does is it becomes what we call delocalized. And delocalized is another word for free to move. So what happens is we arrange our carbon structures with these 3 bonds in layers, and you can see here this is the top layer and we have a bottom layer here, and each of the black dots represents a carbon. So you can see that each one has 3 bonds. And when we're in these layers, we get this 4th electron from each of the carbons becoming delocalized, and that simply means they move in the middle of the layers. So rather than taking part in bonding, they come away from the atom and they exist within these layers, and they're free to move. And it's this delocalization that allows graphite to conduct electricity. And we'll come back to talk about that later when we look at conductivity. Now, our 2 layers have to be held together by some form of attraction, or else they would just completely separate. And similar to our covalent molecular substances, they are held together by weak intermolecular forces. So these dotted lines here in our diagram, these are our intermolecular forces that hold these 2 layers together, and they just sit one on top of the other, and we probably have multiple layers underneath as well, and then we have our delocalized electrons in the center. Now we can also find giant covalent network bonding within boron and silicon compounds, such as silicon dioxide, and similar to what we talked about with our ionic formula, we can look at the chemical formula as the ratio of our atoms. So rather than it just being in our carbon element, we can also find it in these compounds. So if we have SiO2, for example, this is the ratio of silicons to oxygens. It is not that we have one silicon and two oxygens, the way it would be for H2O. That is fixed, whereas the SiO2 is not fixed. It is simply the ratio. Okay, and that's very similar to what we've seen in ionic bonding. The last part of this topic is to look at the properties of these covalent substances. So again, as with ionic, you need to know about their melting and boiling points, conductivity, and their solubility. So we're going to start off by looking at the melting and boiling points. And remember, we're splitting down into two parts because we've got our molecular substances and our giant covalent network substances. So for our molecular, they are going to have low melting and boiling points. The reason why is we are not actually breaking the strong covalent bonds. We are breaking the weak intermolecular bonds. So for example, if you have hydrogen connected to the oxygen to make water, then we're going to get an attraction between the hydrogen and the oxygen, and it is this bond that we are going to break in order to melt or to boil these substances. It is not the covalent bond. So molecular substances have low melting points because we're breaking weak bonds between the molecules. In comparison, our giant network substances have very high melting points, and that is because this time we are breaking the strong covalent bonds. So for example, in diamond, the only bonds that are present are carbon-carbon bonds. So those are the bonds that we are breaking. It is the bonds between the two different carbon atoms that are strong covalent bonds, so they require huge amounts of energy to be broken. The stronger the bond that we are breaking, the higher the temperature required, because the higher the energy that is needed. In terms of conductivity, our molecular substances do not conduct electricity because there are no charged particles that are able to move. Giant networks are also non-conductive, with the exception of graphite, because graphite has those delocalized electrons. If you remember, that means that we've got our layers of our carbons. So we had our two different layers. Remember, they're in our hexagon shapes. I've just drawn them as straight lines to help here. Whereas in the center of those layers, we have those delocalized electrons. And because those delocalized electrons exist, it means that they are free to move, so they can carry charge. Meaning that graphite will conduct electricity, but it is the only covalent substance that we need to know about at this point. In terms of their solubility, again, we don't need to understand the reasons behind the solubility, we just need to know the pattern. So covalent molecular substances will be insoluble in water, but soluble in organic solvents. And our giant covalent substances are insoluble. And the best one to help you remember that is diamond. If we had diamond that was soluble, then that would of course cause problems in terms of jewellery and watches and things that contain these. So diamond is completely insoluble, and you'll have seen that if you know anyone that has a diamond, or if you're lucky enough to own one yourself and it goes near water, then you know that it does not dissolve. So our giant substances are insoluble. Our molecular substances tend to dissolve in organic solvents. So now we can summarise all of our properties for melting point and boiling point, solubility and conductivity for our ionic, our giant network, and our covalent molecular. And this is extremely important, and I strongly suggest that you memorise this, and you should be able to explain why each of these exists, in particular the melting and the boiling point and conductivity. For solubility, you just simply need to know the patterns, so which ones are soluble and which ones are not. But for the others, you have to be able to explain them. So let's finish off by looking at some past paper questions. The first is looking at a structure of silicon dioxide as shown in the diagram. So we have our SiO2 and we've got particle A, which is our grey structure, and we want to say which one it represents. And the easiest way to do that is to look at the numbers. If we count our silicons, or if we count, the black ones, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 of the black. And if we count the grey, we see that we have 28. So that tells us that we have twice the amount of the grey than we do the black, meaning that that must be oxygen. So our particle A is oxygen. And the reasons why is because we have double the amount of them, or we could even say that it's because it forms 2 bonds, or that we have a smaller atom. Any one of those reasons would tell us why particle A is going to be oxygen rather than silicon. And then explaining in terms of its bonding and structure why silicon dioxide has a very high melting point. Now this is for 4 marks, so what we have to do is we're talking about what is the structure, what type of bonding, what is being broken, and why that gives us a high energy or a low energy, and that's where our 4 marks come from. So we have to say that we have covalent bonding, we have a giant structure, or you could even say we have a lattice structure. This means that we are then breaking strong covalent bonds, and then this is very high because this requires large amounts of energy. Now we don't want to say it requires a high temperature because the question tells us that. We have to say what that means in terms of the high temperature, and you should be relating it back to energy. So because we're breaking our strong covalent bonds, then we require a large amount of energy in order to do that, because this is a lattice structure. Then a typical question, this comes up very regularly and it's just a case of memorising the answer. What is meant by the term covalent bonding? Well, it is the electrostatic attraction, because we should always be using that term in our bonding questions. So it's the electrostatic attraction between, and then you just have to say what? Between the shared pair of electrons, and that of course is our negative, and the 2 nuclei. Okay, we don't say nucleuses, we just say nuclei, and that's because that is our positive. You could even potentially draw a diagram if you wanted, where you had your overlap and you had your electrons and your nucleus like that, and you could show that there's an electrostatic attraction here, but the best thing to do is to explain in words. So the electrostatic attraction between the negative shared pair and the positive nuclei. And then we want to draw a dot and cross diagram showing the bonding in a molecule of ethene. Now this question will actually become much easier once you have done the organic topic, because of course these are taken from exams that assume that you have done everything. So I'm going to just help you out with this a little bit. What exists in ethene is it exists as a double bond. So we have a carbon double bonded to another carbon, and then 4 hydrogens like that. So that's what we're going to draw here. So we have our first is our carbon, and then that of course overlaps with another carbon. So we've got 1, 2, 3, 4, and remember we're going to draw those 2 electrons here because we have a double bond with the other carbon, and then we get an overlap with our hydrogen. I'm going to draw them as circles like that, to show that we make those 4 bonds as well. And that is our dot and cross diagram for carbon. Our dot and cross diagram for ethane. Now we've got substance A and substance B, and we're told that they are both covalently bonded and they have simple molecular substances. And the table gives us the boiling points between A and B. So A is negative 42 degrees Celsius and B is minus 0.5. So firstly, we want to explain why substances with simple molecular structures have low boiling points. So again, what are we breaking and what effect does that have? And it's because we break weak intermolecular bonds. This time we're not breaking the strong covalent bonds. And what effect does that have? Is that they require a low energy to break. Now we can't say less energy because less energy would imply that we are comparing it to something else, and we're not doing a comparison here. So we have to use the term low or little or small amount of energy. Don't use the word less unless you're actually comparing two things. And then suggest why the boiling point of B is higher than A. Well, again, this is to do with those intermolecular bonds, and the stronger the intermolecular bonds, the higher the boiling point. So this simply tells us that B has stronger intermolecular bonds. And that just means it requires more energy in order to break those bonds. Now there's the mark scheme for the first set of questions if you've been trying those at home, and then the mark for the second set as well. Now that's everything for the double content for topic 1G, covalent bonding. I would, as I mentioned before, strongly suggest that you practice drawing your dot and cross diagrams and then make sure to memorise the table explaining the summary of the different types of properties depending on their bonding. If you have any questions, please feel free to leave a comment below, and we hope to see you back soon.